All right, welcome to the deep dive. Today we're going deep, really deep, into the heart of modern technology. We're talking about the computer microprocessor.
Oh, yeah, those tiny chips that pretty much run everything around us.
That's right. And, we wouldn't be diving in without some serious guidance. So, big thanks to our listeners. They sent us this fantastic PDF, InsideTheMachine.pdf by John, they call him Hannibal Stokes. It's a gold mine, I tell you. It's packed with insights about how these little brains actually work, from the nuts and bolts of computer parts, the architecture of the chips, to the software side of things.
It's a real deep dive for sure. And I think, whether you're a techie or just someone who's curious about what makes their smartphone or laptop tick, we're going to break it down. We'll give you that moment of understanding how these microprocessors function, what sets apart different designs, and maybe even a few things that might surprise you. No jargon, just the good stuff.
Exactly. No tech speak, just plain English. So let's start with the basics. According to Stokes, what does a computer do at its core? It reads, changes, and stores sequences of numbers. It's kind of like a super fast, super organized file clerk that's constantly crunching numbers and rearranging them based on a specific set of rules.
And the amazing thing is, all the incredible things computers do today, from running complex simulations to streaming movies, boils down to these three simple actions. And to carry out these actions, every computer, no matter how advanced, has three fundamental parts. First, you need memory, the storage where all those numbers are kept. Then there's the arithmetic logic unit, the ALU, that's the workhorse, the part that actually does the math, changing the numbers based on the instructions it receives. Finally, you have the control unit. This is like the conductor of the orchestra, coordinating everything, telling each part what to do and when.
And this leads to a truly revolutionary idea, the stored program concept. Before this, imagine early computers or even calculators. Every calculation required someone to manually input each step, almost like rewiring the machine for each new task.
It was a huge limitation. The stored program concept changed everything. Now, the instructions themselves, the program, could be stored in the computer's memory right alongside the data, ready to be executed whenever needed. This flexibility is what makes computers so powerful and versatile. It's the core of what we call software.
Now, when it comes to speed, it's not just about the ALU. That's where registers come in. Imagine these as super fast VIP storage areas located right next to the ALU. They hold the data that's being actively processed at any given moment. Think of it as the ALU's personal workbench.
Exactly. And in the early days of x86 computers, these workbenches were incredibly small. They only had 8 registers, which is really limited compared to modern processors. You can see the challenge here, balancing the need for the fastest possible access to data with the limitations of physical space.
So we've got the storage and the processing parts, but we need to tell them what to do. And that's where instructions come in. There are essentially two main categories of instructions. First, arithmetic instructions, those are the ones that tell the ALU to do the math, like adding or subtracting numbers. But just as important are memory access instructions.
Absolutely. Memory access instructions are crucial because they allow the processor to get the data it needs from the main memory and also to store the results back into memory. Remember, those registers are tiny, and the computer's main memory is much larger, kind of like a warehouse. Memory access instructions act like the forklift trucks, moving data in and out of that warehouse.
To help illustrate all of this, Stokes uses a simplified imaginary computer model called the DLW1. Just to give us a visual, it has an ALU, 4 registers, we can just call them A, B, C, and D, and then 256 memory slots, each with its own address.
It's a great way to see the core principles, and even in this simplified design, we see techniques that are commonly used in much more complex processors. One of those is register relative addressing. This is like saying, hey, processor, don't go directly to memory location number 50. Instead, go to the address that's 10 slots away from whatever address is currently in register D. This kind of relative addressing is super useful when you're working with large blocks of data in memory.
Now let's talk about the actual language that the computer understands, machine language. These are the raw instructions, written in binary, just strings of ones and zeros. They got the processor what to do and which data to use. Each instruction is a specific combination of these bits. For example, the DLW1 uses a 16-bit format for each of its instructions.
And this is where the concept of code comes in. When we talk about code, we're not just referring to those raw binary instructions. It encompasses any set of instructions written in any programming language, whether it's binary, a slightly more readable form called assembly language, or even high-level languages like Java or Python that programmers use today. They all eventually get translated into that basic machine language that the processor can understand.
So we've got our instructions, our data, and the parts that handle them. Now, how does it all come together? How does the processor actually execute these instructions?
Well, the process begins with something called the instruction fetch. The processor uses a special pointer called the program counter, or PC. Think of it as a little finger that points to the next instruction in the program that needs to be executed. It grabs that instruction from memory and loads it into a special holding area called the instruction register. And once it's fetched, the PC automatically moves to the next instruction in line, just like moving that little finger along a list of instructions.
But programs don't just run straight through from start to finish, do they? There are jumps and loops, decisions to be made along the way.
You're absolutely right. That's where conditional branch instructions come in. These instructions allow the program to make decisions. They check for certain conditions, like whether the result of a calculation is 0. If the condition is true, the program jumps to a different part of the code. If not, it just continues to the next instruction in line.
So how does the processor know if a condition, like a 0 result, is true or not?
That's where a special register called the processor status word, or PSW, comes into play. After the ALU does a calculation, the PSW stores little flags that indicate things like whether the result was 0, positive, negative, or if there was an overflow. So a conditional branch instruction just checks these flags in the PSW to decide what to do next.
Okay, that makes sense. Now here's a question. When you turn on your computer, how does it all begin? There's no program running initially, right?
Right. Well, the microprocessor is hardwired to start by fetching its very first instruction from a specific preset address in memory. And guess what's stored at that address? It's the BIOS, the basic input-output system, a small program that lives on a special chip on the motherboard, a ROM chip. It does all the essential startup routines, making sure everything is working properly before the computer loads the operating system and you see the familiar boot screen.
Now let's zoom in on the CPU itself. It's often divided internally for efficiency. There's this notion of a front end and a back end.
Exactly. Imagine it as a two-part assembly line. The front end is responsible for fetching the instructions from memory and decoding them, figuring out what they mean. It's like translating the instructions into a language the rest of the CPU can understand. The back end, which includes the ALU and the registers, is where the action happens. It's where the calculations are performed and the data is manipulated. Instructions flow from the front to the back to be processed.
And Stokes describes the execution of a single instruction as a four-step process.
Right. First, you have the fetch phase, where the instruction is grabbed from memory. Then comes the decode phase, where the processor figures out what the instruction means. Next is the execute phase, where the ALU actually performs the operation. And finally, there's the write-back phase, where the result is stored back into a register or memory. These four phases form the basic rhythm of a processor, repeated billions of times per second for every single thing your computer does.
So that's the single instruction cycle. But processors are insanely fast. How do they achieve that speed? This is where pipelining comes in, right?
Precisely. Think of an SUV factory. Let's say there are 5 steps to building an SUV: chassis, engine, bodywork, wheels, and paint. Now, if you do it one step at a time, or only starting the next step after the previous one is complete, it'll take forever to build a bunch of SUVs. That's the non-pipelined approach.
So it's a very linear process, one SUV at a time.
Right, but with pipelining, things change. Once the chassis team finishes the chassis of one SUV, they immediately start working on the chassis of the next one. At the same time, the engine team is working on the engine of the first SUV, and so on. You've got multiple SUVs in different stages of production, all moving down the line simultaneously. This way, you can produce a finished SUV much faster.
So how does this translate to processors and instructions?
Well, just like the SUV assembly line, we can break down instruction execution into separate stages, like the 4 phases we just discussed: fetch, decode, execute, write back. A pipeline processor doesn't wait for one instruction to finish all 4 stages before starting the next one. It has multiple instructions in different stages at the same time, flowing through the pipeline.
And the number of these stages is called the pipeline depth. So a processor with our 4 stages has a depth of 4.
Exactly. Imagine each stage takes just 1 nanosecond. In a non-pipeline processor, a single instruction would take 4 nanoseconds to complete. But with a 4-stage pipeline, once the pipeline is full, you can finish 1 instruction every nanosecond. It's a huge speed boost.
Pipelining sounds amazing. But like any clever trick, there must be some downsides or trade-offs.
Of course. Pipelining comes with added complexity. You need more circuitry to keep track of everything, buffers to hold instructions and data as they move through the stages, and all of this requires more transistors, taking up more space on the chip. And as you make the pipeline deeper, the overhead increases. Deeper pipelines, like the Pentium 4's incredibly deep 20-stage pipeline, can face significant challenges in managing all of that complexity.
Let's talk about the different kinds of instructions that processors handle. This leads us to the concept of instruction set architecture, or ISA.
The ISA is like the programmer's view of the processor, the interface they use. It defines things like the available registers, the memory organization, and most importantly, the set of instructions the programmer can use to write software for that processor. Remember our DLW1 that had a very simple ISA with its 4 registers and limited instruction set.
But you mentioned a DLW2, which had the same ISA but a different internal design.
Right, that's a key distinction. The ISA is like the blueprint, while the actual physical implementation of the processor, the microarchitecture, can vary even if they share the same ISA. The DLW2, for example, had 2 ALUs, allowing it to potentially execute 2 instructions at the same time, a concept called super-scalar architecture. Think of it as having multiple cooks in the kitchen working on different parts of a meal simultaneously.
It seems like in the early days of computing, software had to be specifically written for each type of hardware. That must have been a nightmare for developers.
It was. Every time a new computer came out with a different internal design, programmers often had to rewrite their programs from scratch. It made software development incredibly time-consuming and expensive. There was no way to easily port programs from one machine to another.
So how did they solve this problem?
The breakthrough came with IBM's System 360 in the 1960s. They introduced the ISA as a clear dividing line, an abstraction layer between software and hardware. Now, programmers could write code targeting a specific ISA, and that code could theoretically run on any machine that implemented that same ISA, regardless of its specific internal design. This was a huge step towards software portability.
And this standardization of ISAs then led to different design philosophies, CISC and RISC.
Exactly. CISC, which stands for Complex Instruction Set Computing, is typified by older architectures like the x86. These ISAs often had a large and complex set of instructions, some of which could perform fairly complicated operations in a single instruction. RSC, or Reduced Instruction Set Computing, took a different approach. Architectures like PowerPC, MIPS, and ARM championed the idea of having a smaller, simpler, and more uniform set of instructions.
So RSC basically shifted the complexity from the hardware into the software.
That's the idea. RSC architectures aim to simplify the hardware by having simpler, fixed-length instructions that could be executed quickly and efficiently. They relied on high-level programming languages and compilers to break down complex tasks into sequences of these simpler instructions. It was a trade-off. Simpler hardware could lead to higher performance and lower power consumption, but it sometimes meant that programmers had to write slightly more complex code or rely on more sophisticated compilers to achieve the same results.
You mentioned register renaming earlier. How does that work in superscalar architectures?
In a superscalar processor with multiple execution units, you might have a situation where 2 instructions in the program try to access the same register, creating a bottleneck. Register renaming is a technique where the processor internally maps those programmer-visible register names to a much larger pool of physical registers that are hidden from the programmer. This way, even if 2 instructions in the code appear to be using the same register, the processor can assign them to different physical registers, allowing them to run simultaneously without conflict.
And to manage this larger set of physical registers, processors use something called register files.
Exactly. A register file is like a small, super-fast memory array that holds all those physical registers. It's designed with multiple ports, so multiple execution units can access different registers at the same time without interfering with each other. It's a vital part of making those superscalar designs work efficiently.
All right, so we're getting a sense of just how intricate the CPU is. Now, all this processing power needs data to work with, and that data comes from memory. But accessing main memory can be slow. This is where the memory hierarchy and caching become crucial.
Absolutely. In a computer system, you have a hierarchy of memory organized by speed and cost. At the top, closest to the CPU and the fastest, but also the smallest and most expensive, are the registers. Then you have different levels of cache, level 1, level 2, L2, sometimes even level 3, L3. Further down is the main system memory, or RAM. And finally, the slowest but largest and cheapest storage, the hard disk or solid-state drive.
And the caches L1 and L2 are often built right onto the CPU chip itself for speed, right?
Yes, that's the standard approach nowadays. Having the caches on the same piece of silicon as the processor dramatically reduces the time it takes to access frequently used data and instructions. And this is crucial because CPUs are so fast that they would spend most of their time just waiting for data if they had to constantly access the much slower main memory.
When the processor encounters a branch instruction where the program might go one of 2 ways, how does it handle that uncertainty to avoid falling the pipeline?
Branch prediction is the key. Processors use various techniques to try and predict which way a branch will go. Some use simple rules called static prediction. Others use more sophisticated methods like dynamic prediction, where they keep track of past branch decisions to make better guesses. If the prediction is correct, the processor can speculatively execute instructions along the predicted path. saving time and keeping the pipeline flowing smoothly. But if the prediction is wrong, it has to discard those speculatively executed instructions, which can cause a performance hit. For example, the Pentium used a combination of static and dynamic prediction techniques.
You also mentioned floating point operations, those that deal with numbers with decimals, as being more complex than integer operations.
Floating point operations are more complex because they involve more intricate calculations, so their execution pipelines are often longer. For instance, the Pentium had a 6-stage pipeline for floating point calculations compared to its shorter pipeline for integer operations. Early x86 processors also used a somewhat peculiar floating point architecture called the x87, which had a register file that worked like a stack, making programming a bit more challenging in some cases.
Okay, so to keep those pipelines running smoothly, especially with complex instructions, modern processors use a technique called out-of-order execution.
Exactly. Instead of vividly executing instructions in the exact order they appear in a program, out-of-order execution allows the processor to look ahead and execute instructions if the data they need is ready, even if they're further down in the program sequence. This way, it can keep its execution units busy and avoid stalls caused by dependencies between instructions.
But how does it ensure that the final results are still produced in the correct order?
It uses dynamic scheduling and special structures like the reservation station and the reorder buffer. In the P6 microarchitecture, for example, decoded instructions are placed in a reservation station where they wait until their data is available. Once ready, they can be issued to the execution units in any order. The reorder buffer then acts like a log, keeping track of the original instruction order and making sure that their results are committed, meaning written back to memory or registers, in the correct sequence. So while the processor might be juggling things internally to the outside world, it still appeared as if everything is happening in the correct sequential order.
So it's all about maintaining the illusion of sequential execution, even though things might be happening quite differently under the hood.
Right. It's a powerful technique for achieving high performance, but it also adds more complexity. And in processors with very deep pipelines, like the P6, if a branch prediction turns out to be wrong, the performance penalty of flushing the pipeline and restarting becomes more significant.
The P6 also did something called instruction set translation, right?
Yes, it's a technique used to handle complex ISAs like x86, which has variable length instructions and lots of different formats. Processors like the P6 would translate these complex 86 instructions into simpler, fixed-length microoperations, which are much easier for the internal execution units to handle. This translation adds an extra step in the decode phase, but ultimately it streamlines the execution pipeline.
All right, let's get back to RSC versus CISC with some concrete examples.
The x86 architecture, as used in Intel's Pentiums, is a classic example of CISC. It's known for its variable length instructions, multiple instruction formats, and powerful instructions that can sometimes perform complex tasks in a single step. PowerPC, on the other hand, embodies the RSC philosophy. It uses fixed-length instructions, has fewer formats, and follows a load-store model, meaning data must be explicitly loaded into registers before it can be operated on.
So what are the pros and cons of each approach?
CISC can sometimes lead to higher code density, meaning that programs might need fewer instructions overall, which can save memory space. And for some specific complex operations, like string manipulations, writing assembly code for CISC can be a bit simpler because there might be single instructions that directly handle those tasks. But the complexity of CISC instructions can make them harder for the processor to decode, schedule, and execute efficiently. RSC architectures, with their simpler and more uniform instructions, aim for speed and efficiency in the hardware. They rely on compilers to translate complex tasks into sequences of simpler instructions.
And this need to support the legacy x86 ISA came with a cost for processors like the P6, didn't it?
Yes, it did. A significant portion of the P6's transistors were dedicated to the complex decoding and translation logic needed to handle the x86 instruction set. This impacted other aspects of the design, such as the size of the on-chip caches. RSC processors, with their simpler front ends, often had more room for larger caches, which could give them a performance advantage in certain scenarios.
The Pentium 2, despite these challenges, managed to compete reasonably well and even gain some ground in the server and workstation market.
The Pentium 2's back end, the part that actually executes the instructions, was actually quite good. Its overall performance for both integer and floating point operations was competitive within the CISC landscape at the time. However, RSC architectures with similar manufacturing technology often had the potential for higher raw performance due to their inherent design simplicity. The x86's strength of that time often lay more in its cost-effectiveness and the huge existing software ecosystem that it supported.
And then came the Pentium the third, which introduced the streaming SIMD extensions, or SSE.
SSE was a major addition to the x86 instruction set. It brought single instruction, multiple data, or SIMD capabilities to the x86 world, specifically for floating point operations. This meant that the processor could now perform the same operation on multiple pieces of data simultaneously, which significantly boosted performance for multimedia tasks like image and video processing and scientific computing that often involves working on large arrays of numbers.
Okay, let's switch gears back to RAC and talk about the PowerPC architecture. You mentioned something called the instruction queue. What was its role?
In the PowerPC 601, for example, the front end could fetch up to 8 instructions and put them into a queue. This queue acted as a buffer, allowing the processor to analyze the upcoming instructions and make some decisions. The branch processing unit could look ahead in the queue, identify branch instructions, and sometimes even eliminate them entirely through a technique called branch folding, which saved time and helped to avoid pipeline stalls.
You also said that PowerPC has a condition register, like the Pentium's PFW, but with more flexibility.
The PowerPC Condition Register, or CR, serves a similar purpose to the PSW, storing information about the results of arithmetic operations. But the CR is more flexible in terms of how its flags are set by instructions and how they can be checked by subsequent branch instructions. It gives programmers more fine-grained control over the flow of execution.
We mentioned several PowerPC models, the 601, 603, E604, and the 750, also known as the G3. Can you highlight some of their key differences?
PowerPC 601 was a high-performance processor, strong in floating point with a good-sized L1 cache. The 603 and 603E aimed for low power consumption and were often used in portables. They used a shallower pipeline compared to the 601. The 604 aimed for higher clock speeds with a deeper pipeline and a wider back end with reservation stations for out-of-order execution. Then came the G3, which was based on the 603-603's shallower pipeline, but had significant improvements in branch prediction, often outperforming even the 604E in many real-world benchmarks.
And then we get the G4, which introduced the Altivec SIMD extensions.
Altivec was a game-changer for multimedia processing on PowerPC. It added a whole set of instructions designed for LSIMD operations, along with dedicated vector registers and execution units. The G4 initially had a single vector ALU, but the G4E expanded on that with multiple vector ALUs for even greater parallelism. This wide and shallow approach, with more execution units and a relatively short pipeline, contrasted with Intel's narrow and deep philosophy embodied in the Pentium 4.
Let's delve into that contrast, the Pentium 4 versus the G4E.
The Pentium 4 went for an incredibly deep pipeline, about 20 stages, with the goal of achieving very high clock speeds. They were really pushing for maximum megahertz, sometimes referred to as the megahertz myth or speed addiction. The G4E, on the other hand, had a much shorter pipeline, usually around 7 stages. Its focus was on having a wider backend, meaning more execution units that could work in parallel. It's like the difference between having a single, very fast worker versus having a team of slightly slower workers working together.
And what were the trade-offs of these different philosophies?
The Pentium 4's deep pipeline made it susceptible to performance drops caused by branch mispredictions and cache misses. In a long pipeline, if a prediction is wrong, you've wasted a lot of work and have to refill the pipeline, which takes time. The G4E's shorter pipeline was less affected by mispredictions, and its wider back end was well suited to tasks that could be parallelized.
How did their floating point units compare?
The G4E's FPU was relatively straightforward, relying on its vector units for much of the heavy lifting. The Pentium 4's FPU, while benefiting from high clock speeds, had higher latencies, meaning it took longer to complete individual floating point operations. However, it could still achieve high throughput due to the high clock frequency.
You mentioned vector operations. What are intra-element and inter-element operations in SIMD?
In SIMD, you're working on multiple data elements simultaneously using vectors. Intra-element operations work on corresponding elements within 2 or more vectors, like adding the first element of one vector to the first element of another vector. Intra-element operations are those that happen within a single vector, such as adding up all the elements of a vector to get a single sum.
Both the G4E with Altivec and the Pentium line with SAC supported these operations.
Yes, Altivec provided a rich set of both intra- and inter-element vector instructions with dedicated vector registers and execution units. Intel's SSE extensions, introduced with the Pentium 3, brought similar capabilities for SMD floating point operations to the x86 architecture.
Now let's talk about the transition to 64-bit architectures.
Intel initially tried a whole new 64-bit ISA called IA64, used in their Itanium processors. It was based on a different approach called explicitly parallel instruction computing, or EPFC, but it faced challenges and didn't take off in the mainstream market. AMD, on the other hand, developed x86-64, a set of extensions that were backward compatible with the existing 32-bit x86 ISA. This turned out to be a brilliant move for AMD.
What was the main motivation behind moving to 64-bit computing?
Two key reasons. First, wider registers allowed processors to handle larger chunks of data at once. Second, and maybe even more important, 64-bit addressing broke the 4 GB memory limit of 32-bit systems. This was crucial because applications and datasets were growing larger, and being restricted to 4 GB of addressable RAM was becoming a bottleneck.
So it wasn't just about bigger numbers, but also about accessing more memory.
Exactly. 64-bit architectures brought wider ALUs, but the ability to directly address a much larger amount of RAM was a key driving force. And AMD's x86-64 went beyond just wider registers. It increased the number of general-purpose registers and XMM registers, and extended the program counter to handle those larger addresses.
And how did it maintain backward compatibility with older software?
x86-64 used a system of nested modes. Legacy mode makes it act like a regular 32-bit x86 processor. Compatibility mode allows a 64-bit operating system to run 32-bit programs, and then there's the full 64-bit mode that unlocks all the new features.
Did this jump to 64 bits make programs significantly larger?
Not really. While there might be a slight increase, it was generally less than 10% on average.
Now, about the PowerPC 970, also called the G5, how did it compare to the G4E and Pentium 4?
The 970 was a bit of an operate. It had a fairly deep 14-stage pipeline like the Pentium 4, but also a very wide backend like the G4. It had a massive instruction window that could hold up to 200 instructions, giving it a lot of room for out-of-order execution.
How about its caching system compared to the G4E?
It generally had larger caches, a bigger L1 instruction cache, a similar L1 data cache, and a noticeably bigger L2 cache. It also had a fast front-side bus and supported data prefetching, making it very well suited for handling large amounts of data.
What about its instruction dispatch rules and those IOP groups?
The 970 grouped instructions into groups of up to 5, called IOP groups. These groups had to be formed in a program order, and branch instructions had to go in the last slot. While this might have simplified the dispatch logic, it could lead to inefficiencies if instructions didn't align nicely into those groups, or if a branch wasn't ready to fill that last slot. It reduced the flexibility of instruction dispatch.
How about its imager units? Did it also use specialized simple and complex units like the Pentium 4 and G4E?
It did. It had 2 imager units, with one dedicated to handling more complex operations like division. This allowed it to execute common instructions quickly, while still being able to handle those more complex cases when needed.
And what about its load store unit and the PowerPC condition register?
It had 2 load store units, double the bandwidth of the G4E, which was important for feeding its large instruction window. The PowerPC condition register, or CR, provided a flexible way to store and check the results of arithmetic operations, influencing program flow.
You mentioned the 970's interleaved logical issue queues.
It had 2 logical issue queues, each composed of 2 physical queues. Instructions within a logical queue would be issued in order, but the 2 logical queues could issue instructions out of order with respect to each other. This provided some flexibility while still respecting program order within each logical stream.
Now let's dive deep into caching. You gave a great analogy earlier about a furniture maker in a lumber yard. Can you explain why caching is so essential?
Imagine a furniture maker who needs lumber from a lumber yard. If the lumberyard is far away, the furniture maker has to wait a long time for deliveries, slowing down the work. That's like the CPU waiting for data from main memory. Caching is like having a small, well-stocked lumberyard right next door to the furniture maker's workshop. If the needed lumber is there, it's a quick grab. If not, they have to go to the further lumberyard, which takes more time.
So caching is all about minimizing those trips to the faraway lumberyard.
Exactly. The cache holds copies of data and instructions that the CPU is likely to need soon. If the CPU needs something and it's in the cache, a cache hit, it's very fast access. If it's not there, a cache miss, the CPU has to go down the memory hierarchy, which is much slower. The goal is to maximize hits and minimize misses.
What happens when the CPU requests data?
It first checks the L1 cache, the fastest and closest. If not there, it checks the L2 cache, which is bigger but slightly slower. If still not found, it goes to main memory, RAM. And in the worst case, if it's not even in RAM, it has to be fetched from the hard drive, which is incredibly slow.
Caching relies on locality of reference, right?
Yes, the idea that programs tend to access memory locations that are close to each other, spatial locality, or that were recently accessed, temporal locality. For example, reading a video file sequentially exhibits spatial locality. Accessing the same variable repeatedly in a loop shows temporal locality.
Can you give more examples of spatial and temporal locality in both data and instructions?
Sure. For spatial locality of data, think of streaming a music file. The CPU reads a continuous block of data. For spatial locality of code, some programs have small, frequently used code sections, like kernels in graphics processing. For temporal locality of code, loops are a great example where the same instructions are executed repeatedly. For temporal locality of data, the working set of an application, the data it's currently using, is likely to be accessed repeatedly.
What about cache pollution?
It's when data that's unlikely to be needed again soon gets loaded into the cache, potentially evicting data that would have been useful, like an MP3 player filling the cache with parts of a song that have already been played and won't be needed again.
Now, about cache organization, you mentioned direct mapping and set associative mapping.
There are different ways of deciding where in the cache to store a block of data. Direct mapping assigns each memory block to one specific location in the cache. This is simple but can lead to conflicts if multiple frequently used blocks map to the same location. Set associative mapping divides the cache into sets, and each block can go into any of a few locations within its set. It's more flexible and reduces conflicts.
So there's a trade-off between flexibility and speed.
Yes. Higher associativity, meaning more potential locations per set, reduces conflicts but also increases access time because the system has to check more tags to see if the data is present.
And when the cache is full, how does it decide what to remove?
That's the job of cache replacement policies. The most common one is least recently used, LRU, which evicts the block that hasn't been used for the longest time. The goal is to keep the most frequently used data in the cache.
What are the different kinds of cache misses?
Compulsory misses happen the first time a block is accessed. Conflict misses occur when multiple blocks compete for the same cache location. And capacity misses happen when the cache is too small to hold all the data needed.
What about power consumption? How does that impact design?
Power consumption is a huge concern. It has two main components: dynamic power, which comes from transistors switching on and off during computation, and static power, which is due to leakage current even when transistors are off. As transistors have gotten smaller, leakage has become more significant.
What about the Pentium M and the Core Duo Solo, which focused on power efficiency?
The Pentium M improved instruction decoding with a technique called micro-ops fusion, where certain combinations of instructions were combined internally for efficiency. Core Duo Solo built upon that, extending micro-ops fusion to SSE instructions. They also
All right, welcome to another Deep Dives. Today we have a really fascinating stack of material about how to write high-quality software.
Yeah, so much more than just making the code work, right?
Exactly. It's really all about extracting those nuggets of wisdom to craft code that's not as functional, but also understandable, robust, and, something that can be maintained without wanting to pull your hair out.
I think it's going to be a rapid induction into the minds of exceptional programmers. Like, how do they think? What makes their code special?
That's exactly what we're after. And you've given me such a variety of sources. They touch on so many aspects, from like the super nitty-gritty details of how to write, individual lines of code, to those big picture strategic considerations like managing a whole dev team and how to run a software project. We're going to be drawing from discussions on everything from defensive programming and how you present your code to naming conventions, documentation, handling errors, testing, debugging, build processes, performance, security, software design, architecture, development methodologies, and even how these ideas play out in different domains of programming.
It's like a whole buffet of software development goodness.
It really is. So this is your shortcut, our listeners' shortcut to understanding what makes code truly good. Not just like adequate or functional, but genuinely excellent. Expect lots of aha moments as we connect those dots between concepts that might seem totally unrelated at first glance. And by the end, you'll have a much clearer picture of the underlying craftsmanship that truly sets those professional programmers apart.
I'm excited to get started.
Me too. So let's kick things off by examining the fundamental mindset. One thing that really jumps out from the material is that exceptional programmers, they seem to have a very specific approach. It's not just about raw technical skills.
It's like they have this attitude, this philosophy about coding that goes beyond syntax and algorithms.
Yeah, and a lot of your sources emphasize that it's about creating code that's not just functional, but well written, almost like elegant in a way. It's code that's inherently understandable and less prone to those nasty bugs.
You build that robustness in from the beginning. It's not an afterthought.
Right. It's not just about solving the immediate problem, but doing it in a way that's, going to stand the test of time. Code that others, or even you, 6 months down the line, can understand and build upon. You shared this book, Codecraft, which really resonated with me. It seems like a central question these master programmers are always asking is, if another developer looked at my code, would they immediately grasp what it's doing and why?
Precisely. Could they understand the logic and the purpose without needing pages of comments? And I think that's a great segue into the concept of defensive programming.
Okay, defensive programming. Now, your sources describe this as a proactive approach. It's less about fixing bugs after they've appeared and more about preventing them in the first place. It's like taking a preventative approach to coding.
It's contrasted with debugging, which is what most people think of when they think about dealing with errors. But defensive programming is all about anticipating potential problems as you're actually writing the code.
So constantly asking yourself, what could possibly go wrong here with every single line you write?
Exactly. And there's this really practical recommendation that keeps popping up, which is to always enable all compiler warnings.
Oh yeah, those warnings can be super helpful.
It's like the compiler's trying to give you hints about potential weaknesses in your code before you even run it. Like it's saying, hey, this might not be what you intended.
You gave an example, I think it was in C or C++A, about uninitialized variables.
Yeah, using a variable before you've given it a value, if the compiler catches that for you, it's so much better than having to track down some weird behavior later.
Absolutely. And your material had this whole section, I think they called it Say When, which is all about encouraging developers to really think critically about when they should be using those defensive programming techniques.
And the point they make is it shouldn't be just for when you're working with like unfamiliar code or when you're in a part of the program where you expect errors to happen. It should be ingrained in how you approach every single line of code.
It should be like a core part of your coding philosophy, right?
Exactly. So let's talk about some of the concrete ways you can actually put defensive programming into practice.
All right, practical tips, I like it. Your sources mention a few specific examples.
One really important area is the data structures you choose to work with. For instance, in C++2, using the string class instead of those raw character arrays can significantly reduce the risk of buffer overflows.
Buffer overflows, those could be nasty.
They really can, and the string class helps because it manages its own memory, so you're less likely to accidentally write past the end of the allocated space.
And that can lead to all sorts of unpredictable problems.
Oh, absolutely. And speaking of preventing those kinds of overwrites, when you are working with those potentially unsafe data types, like those raw character arrays, it's crucial to use safe operations.
So, what are some examples of that?
Well, one classic example in C is using stringkey instead of stringkey.
Okay, stringkey, I remember that one.
It's all about setting those boundaries. StringPy, it just blindly copies everything until it hits a null terminator, and that could potentially go way beyond the space you've allocated.
Right, overwriting whatever's in memory after that.
Exactly. But with stringkey, you explicitly provide a limit on the number of characters to copy, so you're in control.
That's a great example of that prevention over cure approach.
Absolutely. And another thing your material emphasizes, which is often overlooked, is checking the return value of every single function call.
Even the ones that seem super basic and likely to fail.
Especially those. Functions can fail for all sorts of reasons. Maybe a resource isn't available or there's some unexpected input. And if you just ignore those failure indicators, you're setting yourself up for trouble down the line.
I guess those silent errors can be the hardest ones to track down.
Oh, definitely. Another technique that comes up is declaring your variables as late as possible right before you actually need to use them.
Oh, I've heard of that. It's supposed to make your code cleaner, right?
It does, but it also contributes to defensive programming. By limiting the scope of a variable, you're reducing the chances of accidentally modifying it or using it incorrectly somewhere else in the code.
So it's like keeping your workbench tidy. Only have the tools you need out at any given time.
That's a great analogy. And speaking of checks and balances, your sources delve into the use of assertions.
Assertions. Are those like checks that are typically used during development to make sure certain conditions are true?
Exactly. They're a way to verify assumptions you're making about the state of your program. But here's the crucial thing. Assertions are usually disabled in production builds.
So the end user never sees them.
Yeah, they're mainly for the developers, so you should never rely on assertions for critical error handling.
Like if a memory allocation fails or something like that.
Exactly. Those kinds of errors need to be handled with robust code that's always active, not just during development.
Okay, that's an important distinction. Assertions are for developers, not for saving the program from a crash. The material also poses some really interesting questions about defensive programming in general.
Right, like can you actually have too much defensive programming? Is it possible to go overboard with the checks and make your code harder to read or impact performance?
And is it always a good idea to add an assertion every time you fix a bug?
They also bring up the whole debate about exceptions versus those more traditional C-style assertions.
Oh yeah, exceptions. I think those are more common in object-oriented languages, right?
Yeah, but not all languages support them. And then they talk about where defensive checks should be placed, whether it's inside functions or around the calls to those functions.
It really gets you thinking about the best ways to write robust and reliable code.
And ultimately, on a personal level, the material encourages you to really examine how carefully you consider each statement you write. Do you relentlessly check those return codes even when you think a function can't possibly fail?
It's about building those good habits and not assuming everything will always go smoothly. All right, so let's shift gears a bit and talk about something that doesn't change what the code does, but has a big impact on how easily it's understood.
You mean code presentation?
Exactly. Formatting, indentation, all those things that some programmers might consider just aesthetic choices.
But your sources argue, quite convincingly, that they actually play a huge role in the overall readability and maintainability of the code.
Makes sense. Well-formatted code can reveal the underlying structure, like it's almost like a visual guide to how the logic flows. But poorly formatted code, it can just be a nightmare to try to decipher.
And even if you're working on a personal project, just for fun, developing good habits with code formatting is a valuable investment.
So it's not just about making things look pretty.
Right. It's about treating your code as a document that's intended for human consumption. And that human might be a colleague, a reviewer, or even just your future self.
I know, I've looked back at my old code and wondered, what was I thinking?
We've all been there. The material even gets into the details of different brace placement styles, like the Ullman style versus the Kernighan and Ritchie style.
Oh yeah, I remember those debates from back in the day. It's like, where do those curly braces go?
And the point isn't to say that one style is inherently superior. It's more about understanding the different conventions that exist in the languages you use and being able to appreciate the choices that have been made in different code bases.
It's like being multilingual in terms of code style.
Exactly. But when it comes to working in teams, there's a strong emphasis on choosing one consistent style and sticking to it.
Otherwise, you get those endless debates and arguments about indentation.
They even jokingly refer to it as programmer civil war.
Programmer civil war, that's a great image. So, how does a team go about actually establishing a coding standard?
They lay out a pretty practical process. It starts with defining the scope of the standard. Is it just about formatting, or does it go deeper into language usage and specific best practices?
I guess starting with something more manageable, like just formatting, might be a good first step.
Right. And then there's the crucial step of getting buy-in from the entire team. If people feel like they've had a voice in creating the standard, they're going to be much more likely to actually follow it.
It makes sense to explain the benefits of code consistency, like improved readability and fewer errors.
Exactly. And then the standard itself should be developed iteratively, allowing for feedback and adjustments along the way. And finally, you need a plan for dealing with existing code that doesn't adhere to the new standard. Do you go back and reformat everything? Do you just apply it going forward? These are all things to consider.
And on a personal level, the material asks, does your code follow a defined style? Do you think it's a good one? Are you consistent across different projects? It really gets you thinking about those habits and choices we make as programmers.
Okay, let's move on to something that I think is so fundamental to writing clear, maintainable code. The power of names.
Ah, yes, naming things. It might seem like a trivial thing, but you're right. Those names can make a huge difference.
Absolutely. A well-chosen name can act as a little piece of documentation. And the core principle that keeps coming up is to favor clarity over brevity.
So resist the urge to use those super short, cryptic abbreviations.
Exactly. Using natural language words makes the code so much more understandable. For example, instead of something like COT, which who knows what that stands for?
Yeah, it could mean anything.
Exactly. It's much better to just write out customer order total. It takes a few extra keystrokes, but the clarity you gain is worth it.
I guess the exception would be for those really short-lived variables like loop counters in small loops.
Right. In those cases, overly verbose names can actually make the code more cluttered. but for most things, err on the side of being explicit.
Be kind to your future self and anyone else who might have to read your code. The material also talks about having a naming convention to distinguish between different types of things like variables and types.
That's right. Having that consistency helps to reduce ambiguity and allows someone reading the code to instantly understand what something is just by looking at its name.
Oh yeah, I've seen code bases where it's like, is this a variable, a function, a constant? Who knows?
Exactly. And when it comes to naming functions, the recommendation is to use a word or a phrase that clearly describes what the function does, but from an external perspective.
What do you mean by external perspective?
Like, focus on the logical operation, not the implementation details. Imagine a function called apples. What does that even tell you? Does it count apples, sort apples, bake apples into a pie?
It's totally ambiguous. You have no idea what it's actually doing.
Right. A better name might be calculate total apples or sort totals besides. Be explicit about the intent.
I like that. Clear and concise. The sources also touch on this interesting and often debated topic of Hungarian notation. Can you explain that one for our listeners?
Hungarian notation is this convention where you prefix variable names with information about their data type.
So like strt for a string or int for an integer.
Exactly. It originated at Microsoft and was quite popular in the old Windows APIs and MFC.
I think I've seen it in some older code bases.
Yeah, the idea was that seeing the type right there in the name could help with readability and even prevent some type-related errors. But these days, it's pretty controversial.
I could see how it could be helpful, but also kind of clunky and maybe redundant.
Right. Modern IDEs already display type information, so the notation can feel like overkill. And it can make refactoring more complicated because if you change a variable's type, you have to rename it everywhere.
I guess it's a matter of finding the right balance between being explicit and not overdoing it.
They also talk about naming conventions for namespaces and packages, basically saying they should reflect the logical grouping of their contents, and the common practice of using all caps for macro names in C and C++A to make them stand out visually.
Those macros can really transform the code, so it makes sense to make them obvious.
And in the mull it over section for this topic, they have some great questions, like, do your names clearly communicate the purpose of the things they represent? Do you prioritize clarity over brevity? And do you follow the naming conventions of your language's standard library? It really challenges you to think about how you name things and why.
It's a good reminder to be intentional with our names and make them work for us, not against us. Okay, let's dive into this idea of writing self-documenting code.
Ah, yes, the holy grail. Code that's so clear and well-structured that it barely needs any external documentation.
Sounds like a dream.
It can be challenging, but your sources outline some strategies for getting closer to that idea. One of the starting points is acknowledging the limitations of traditional documentation. It takes time to create, it often gets outdated quickly, and keeping it synchronized with the code can be a nightmare.
So the idea is to make the code itself as inherently understandable as possible.
Exactly. Reduce the need for those external explanations. There's this really interesting analogy in the material between the structure of a book with its chapters, paragraphs, and sentences, and the organization of code with its files, blocks, and statements.
Oh, I like that analogy. A well-organized book makes it easier to follow the narrative, and well-structured code makes it easier to understand the program's logic.
That's the key. And they talk about specific techniques like ordering declarations within a class so that the public interface is presented first, followed by the private implementation details.
Kind of like show the reader the important stuff up front, and then they can dig deeper into the details if they need to.
Exactly. And another approach they mention is hiding non-essential information, like using the pimple idiom in C++E to conceal the private parts of a class from the outside world.
So the idea is that the reader doesn't need to be bogged down with those implementation details unless they specifically want to dive in.
Right. And while self-documenting code might seem effortless, like it just flowed out of the programmer's mind, it actually requires a lot of careful thought about how to best communicate the program's intent.
It's about making the code tell its own story.
Exactly. They also briefly mention literate programming.
Literate programming, I think I've heard of that, but I'm not entirely sure what it is.
It's basically a way of writing code that's more like writing prose. You're explaining the logic and the reasoning as you go, and the code snippets are woven into that narrative.
So it's more about telling a story rather than just writing instructions for a computer.
Exactly. They also touch on documentation tools that can automatically generate API documentation from specially formatted comments in your code.
Those could be pretty helpful, especially for larger projects.
There's a great example in the material where they critique a really simple C function for bubble sort. The original code is super cryptic with short, meaningless variable names, but then they show how, by using more descriptive names and adding a few concise comments, the code becomes so much easier to understand.
That's a perfect illustration. The improved version is like, oh, now I get what's going on.
They also have some discussion points about this documentation tools, like should you be reviewing the generated documentation itself or the comments in the code?
And where should the documentation ideally reside? In the header files, the implementation files, or both?
Right. And then there's the question of whether internal functions, the ones that aren't part of the public API, should also be documented.
So many things to consider. But the underlying principle seems to be that you should strive to write code that doesn't need a lot of external explanation.
Right, and when comments are necessary, the goal is to explain why the code is doing something, not just what it's doing. The code itself should make the what pretty clear.
Okay, that's a good rule of thumb. Explain the why, not the what.
And the Getting Personal reflection asks you to think about what you consider to be the best documented code you've ever encountered. What made it so good? And how does your approach to documentation change depending on the programming language you're using?
It really gets you thinking about the importance of clear communication in code. Okay, let's talk about something that can be a real pain, but is absolutely essential for building reliable software. Handling errors.
Error handling. It's the difference between a program that crashes at the first sign of trouble and one that gracefully recovers and keeps running.
Your sources introduce this concept of exceptions as a mechanism for managing errors in a more structured way. It's about separating the normal flow of execution from those exceptional cases.
Right, and not all languages have exceptions built in. They also talk about the idea of a function's contract.
Contract, like a legal agreement.
Kind of. It's what a function promises to do given certain inputs. And when it can't fulfill its promise, maybe because of an error, it can throw an exception to signal that something went wrong.
So it's like the function is raising its hand and saying, hey, I can't do this.
Exactly. And then the language's runtime environment has to figure out what to do with that exception.
It goes looking for a piece of code that knows how to handle that specific type of error.
Right. It walks back up the call stack looking for a try.catch block that's designed to catch those exceptions.
And those catch blocks can then decide how to respond, whether it's retrying the operation, logging the error, or something else.
They also discuss different levels of exception guarantees, like the basic guarantee, which means that even if an exception is thrown, the program will be left in a valid state.
So no corrupt data or anything like that.
Right. Then there's the strong guarantee, which goes even further and ensures that if an exception happens, the program's state is exactly the same as it was before the operation started.
So it's like the operation never even happened.
Exactly. And then there's the no-throw guarantee, which basically promises that the operation will never throw an exception.
That one sounds pretty confident.
But it's not always possible to provide that level of guarantee. So once an error occurs, what are your options?
That's a good question. Your sources outline a few different approaches.
The main strategies are to handle the error locally within the functional block where it happened. Maybe you retry the operation or substitute a default value.
So try to fix the problem right there.
Or you can propagate the error upwards, passing it back to the calling function, which might have more context and be better equipped to deal with it.
It's like delegating the problem to someone higher up the chain of command.
And then there's the approach that they strongly advise against, which is simply ignoring the error.
Ignoring it, that sounds like a recipe for disaster.
Oh, it definitely is. Ignoring errors is one of the biggest sources of bugs and instability in software. They make a good point about what to do when you have to report a fresh problem.
A problem that hasn't been encountered before.
Right. It's crucial to think about cleaning up any resources that were being used, like closing files or releasing memory.
Otherwise, you get memory leaks.
Exactly. And you also want to leave the system in a consistent state. If that's not possible, you need to document the inconsistency really clearly.
So anyone working on that code in the future knows what they're dealing with.
Right. They even ask this tricky question. What about errors that occur within your error handling code?
Oh, wow, that's like an error within an error.
Exactly. It highlights how complex error handling can be and why it needs to be robust at every level.
It's a bit like what happens when the safety net fails.
And the Getting Personal reflection asks you to think about how thorough your own error handling is and how it impacts the overall stability of your software.
It also encourages you to think about whether you approach error handling as an integral part of your coding process or something you tack on at the end.
And a good exercise is to take a function you've recently written and think about all the potential error scenario. How many of those did you actually address?
That's a great way to identify those blind spots in our code.
All right, let's shift gears to something a bit more concrete.
Onto the tools of the trade.
Yes, the programmer's toolkit.
Those essential programs and utilities that we rely on every day to write, test, and manage our code.
They draw a distinction between those standalone command line tools and the more integrated environments you find in modern IDEs.
IDEs, those are like those all-in-one packages with editors, compilers, debuggers, all that stuff.
Exactly. They can be super convenient and productive, especially for beginners. But those command line tools, they often offer more raw power and flexibility.
It's like the difference between using a multi-tool and having a whole set of specialized tools.
Right. And sometimes those specialized tools are just what you need to get the job done right. They also emphasize the importance of the build environment.
The build environment, I guess that refers to all the tools involved in transforming your source code into an executable program.
Exactly. Compilers, linkers, build automation tools like Make. They even mention more specialized tools like AutoConf and AutoMake, which are often used in open source projects to handle a configuration and build process across different systems.
It's like having a set of instructions for how to assemble all the pieces of your software.
And they encourage you to learn both the integrated build environments of IDEs and the individual construction tools to get a deeper understanding of how your software is actually created.
I like that. It's like knowing how to both drive a car and also understanding how the engine works.
Exactly. And the mull-it-over questions ask, which type of tools do you find more powerful, command line or GUI? Are there construction tools that aren't even programs? And what are the most important characteristics of a development tool?
Good questions. And the getting personal reflection encourages you to think about your own tools. How often do you use them? How well do you really know them? And are you maximizing their potential?
It's a good reminder to take stock of our tool set and make sure we're using it effectively.
Okay, let's face it, we all encounter them, so let's talk about bug.
The bane of every programmer's existence. But your sources approach them in a very systematic way.
They start by clarifying the terminology. What's the difference between an error, a fault, and a bug?
An error is a human mistake in our thinking, which leads to a fault, which is the manifestation of that error in the code. And bug is just the common, informal term for a fault. They even have that fun anecdote about the moth in the Mark II Aiken relay calculator.
Oh yeah, the original bug. But beyond the history, they lay out this fundamental principle. The single most important rule of testing is to do it.
It might sound obvious, but it's surprising how often it's neglected. And the responsibility for testing falls squarely on the shoulders of the programmers.
Not on the QA team.
QA's role is to test the overall product, but developers need to thoroughly test their own code before handing it over. Releasing untested code is, as they put it, stupid.
It's like expecting someone else to clean up your mess.
And the emphasis is on testing early and often at all levels of development.
From individual functions to entire systems.
Exactly. And for every test, you should be clear about what code you're testing, the method you're using, and when you can confidently say that testing is complete.
That last one can be tricky, knowing when to stop testing.
They also touch on test-driven development, where you write the tests before you write the code.
That's an interesting concept. It forces you to think about how the code will be used from the outset.
Right. And they talk about the challenges of creating exhaustive test harnesses as software becomes more complex.
You can't manually test every possible scenario.
So automating tests becomes essential. They highlight the value of running unit tests automatically as part of the build process. Tools like Unit can help with that.
So every time you build your software, you're also running a suite of tests to make sure nothing is broken.
And that's especially important for regression testing, making sure that new changes don't inadvertently break existing functionality.
It's like having a safety net for your code. They also categorize runtime errors by how much pain they cause.
From those relatively easy-to-fix syntactic errors that the compiler catches to the more insidious semantic bugs and linker errors.
And interestingly, compilation errors are considered the best kind of error.
Because they're usually the easiest to identify and fix. The longer a fault remains hidden, the more costly it becomes to deal with.
It's like a small crack in a foundation can turn into a huge structural problem if you ignore it.
So they lay out a very methodical approach to bug fixing. First, reproduce the failure reliably. Then, thoroughly understand what's causing the problem.
No jumping to conclusions.
Right. Then, create a test case that clearly demonstrates the bug. And finally, fix it, but make sure you don't introduce any new bugs in the process.
It's like carefully diagnosing a medical condition before prescribing a treatment.
They also reiterate the importance of checking those function return codes and testing all program functionality, especially those edge cases that don't come up very often.
Those edge cases can really bite you.
They also talk about techniques for isolating the faulty component, like commenting out sections of code to narrow down the problem. And they have this great real-world example of a bug that was caused by linking against an older version of an OS library, even though it was supposed to be backward compatible.
It turned out they had to rebuild a third-party library to fix it.
It highlights how complex those dependencies can be. They advise against overusing debuggers.
So don't just jump into the debugger every time something goes wrong.
Right. Try to understand the code first. Debuggers are a last resort for when the behavior is truly inexplicable.
They're more for exploring the runtime behavior of your code, not for replacing the need to think critically.
They also mention other debugging tools like memory access validators, system call tracing, and core dumps.
Core dumps, those are like snapshots of the program's memory at the time of a crash, right?
Exactly. And they also emphasize logging as a really powerful technique for generating information about what's happening inside your program.
That could be super helpful for pinpointing the exact circumstances that led to a failure.
The mull-it-over questions ask, who's better equipped to fix a bug, the original programmer or the person who discovered it? When should you use a debugger versus just thinking it through? What are some good techniques for learning unfamiliar code before you try to fix bugs in it? How do you prevent memory leaks?
Really good questions to ponder. And the Getting Personal Reflection asks, do you test your code thoroughly before committing it? How do you approach debugging? And do you use debugging tools effectively?
Now let's talk about the process of actually building software.
Taking that raw code and turning it into a working application.
And the first point they make is that it's crucial to understand how your project's build system works, especially as projects get larger and more complex.
It's like knowing the recipe for your software.
Exactly. They point out that a lot of programming textbooks gloss over the build process, focusing on those simple single-file examples that don't really reflect real-world development.
So they're doing us a disservice.
In a way, yes. They also talk about the different mechanisms for building executables. Interpreted languages, compiled languages, and byte-compiled languages.
So like Python is interpreted, C++ is compiled, and Java is byte compiled.
Exactly. And each approach has its own build process and tools. They even have this interesting section on building as metaphor.
Building as metaphor.
They draw parallels between software construction and traditional building processes, like laying bricks and mortar versus writing code.
It's a good way to visualize the different stages involved, even if the analogy breaks down in some areas.
Right, and they talk about how the metaphor has influenced things like the software patterns movement.
Patterns, those are like reusable solutions to common design problems, right?
Exactly. They also go into some detail about the characteristics of different language types, like scripting languages, which are often interpreted, tend to have a very fast development cycle and are more forgiving of minor errors.
So they're good for prototyping and quick experimentation.
They mention examples like shell scripts, batch files, and TCL, and then there are compiled languages which use a compiler and a linker to translate the source code into machine instructions.
That's a more involved process.
It is. They talk about the difference between compiling for the same platform and cross-compiling for a different platform.
Like compiling Windows code on a Linux machine?
Exactly. And then there's the whole concept of multi-stage.